Okay, good. So, okay, welcome everybody to our webinar on variational analysis and optimization. This is the set one this semester. And today we have the speaker, as a speaker, Nguyen Cuong. I have always problems with the order of the names because Cuong keeps juggling with the names, putting one name first, the next one. Okay, it's still a finite number of combinations, so not that difficult. Cuong represents Federation University Australia. He is our student, PhD student, and he has almost completed. Basically, he has submitted his thesis and now is eagerly waiting for the reports of the examiners. So if by chance we have examiners in the audience, keep in mind that Cuong is looking forward to receiving your positive reports. Okay, today Cuong is going to talk about transversality properties, and for a change it is about necessary conditions for transversality, which is not quite typical. Normally people deal with sufficient conditions, and I know that Cuong was also involved in developing sufficient conditions, but necessary conditions seems to be his favorite topic. And now we are going to learn about necessary conditions for transversality properties. Please, Cuong, the floor is yours.
Thanks, Alex. Thanks, Alex, for introduction. So first, I would like to thank the organizer for the invitation, and also everybody attending the seminar today. So the topic of my talk today will be about some necessary condition for transversality properties. So in some cases, it's also sufficient. So it's based on the joint work with Alex and Hoa Bui. Hoa Bui is a former PhD student of Alex. So my talk will be divided in 5 parts. First, I will provide a brief introduction, and then I will talk about some primal and dual condition and some connection between transversality and regularity property. And finally, we'll have some time for discussion. This is the topic of a talk. The topic that I want to talk about today belong to a bigger topic that I have learned in the last 3 years. That's the transversality for sets, matrix regularity for separately mapping, and error bar for function. So we see that function or separately mapping and sets play very important role in variational analysis. So take an easy example. When we want to minimizing a problem, then the objective function can be the single value or set value, and the constraint can be sets. So they are fundamentally important in variational analysis and optimization. They are also strongly connected. So although today I will talk about transversality for sets, I also mentioned some connection between transversality and regularity property. So given X is a norm space and 2 sets, and a point X belongs to the intersection. So transversality basically means that the sets have a good position near a point in the intersection. So these properties have many applications in variational analysis. So it can be used for normal calculus, calculus for tangent, normal cone, coderivative, or subdifferential. And it can also apply to convergence analysis for computational methods, and also for they can also be used a qualification condition to provide optimality condition for a constraint optimization problem. So to avoid the possible confusion, so let me talk a little bit about the terminology. So in the past, transversality is usually called regularity, but we follow the name suggested recently by Alex UFA in the book of 2017. So when we mention the regularity for one object, we call it regularity. But for two or more objects, we call transversality. So for instance, we call regularity of a fixed set and transversality of a collection of sets, or transversality of a map into a set. So just want to make it clear. So because the topic of today's talk will be about nonlinear transversality, so let me introduce a nonlinear function. So let's see the family of some of our strictly increasing function satisfy these two conditions. So this is the two formula example for this class of function. That is the power function, or the sum of the power and the linear function. Not that the strictly condition here is needed, because we need the function phi to be invertible. And actually the nonlinear function here is very simple setting. We employ this function. I just want to cover as many as possible existing result in the literature. So some of many of our results are also used in the linear setting. So we also define the subset of C. So given delta, we define C delta is the class of function that satisfy this inequality. Actually, this condition can be made stronger by requiring the function phi minus 1 overall increasing. With our attention, we try to make the assumption as weaker as possible. So we need this condition. So this is an example of this class of function. We have the power function when Q belongs to 0 to 1. So we will need the C delta when we consider the convex case when study transversality derivative. Okay, this is the definition of phi semi-transversality. So we call the collection of sets a phi semi-transversal at the point x bar if we have this condition satisfied for all x1 satisfy this condition. So the condition means that whenever we make the linear translation of the sets near the point of the intersection, so the new intersection become non-empty, and this requirement need to hold uniformly for all raw belong to 0 to delta. And the perturbation vector, it depends on the function phi in this way. Recently, we realized that we can consider the general case of this one instead of study the linear perturbation, linear translation. We can consider the non-linear translation. I mean, we can consider the mapping f of x1 and f of x2 here. So we are working on this paper, and we hope that it can be finished soon. So the study, the repetitive was first studied by Alex in the paper 2005, when he considered this property in the linear case as a negation of the stationary property. And in the Hilbert case, I mean when phi is the power function, is studied by Alex and Tao, who are here today in this paper. This is the definition of subtraversality. We have this intersection, again, how uniformly for our rho and x satisfy the condition. In the past, usually the property is studied just when rho and x depend on just one constant delta. In here, we fix delta and delta 1, and these constants are different because the contribution of the rho and x in the definition of the property is different. So that's the and the constant delta 1 and delta 2 is are carefully computed when we provide the characterization for the property. So the property was first used by Duletsky in 1982 in convergence theory, and in computation, the property is used by Hans Bauske and Nguyen in the paper 1993, when they employed the property as a qualification condition to provide convergent ray for the alternating projection for solving convex feasibility problem, the problem of finding the common point of the given sets. So the third property is called transversality. It is the property is a stronger version than semi-transversality. So we see that instead of requiring the intersection, instead of requiring the non-emptiness of the intersection at the fixed x bar, we require it for our omega 1 and omega 2 belong on the neighborhood of x bar. So in the special case, if the two omegas equal to x bar, this property reduced to the semi-transversality. And again, the perturbation vector, it depends on the function phi in this way. So in the linear or nonlinear case, we always had the implication that transversality is stronger than semi and subtraversality. And there is no connection between the first and the last property. But we will show that in the convex case, there is some connection between these properties. There is some clear connection between the three properties. We will see later. So in the linear case, the property was first studied by Alex in the paper 2005, when it is the negation of the approximate stationary property. So in computation, this property is first used by Lewis, Luke, and Malik in the paper in 2009, when they used the dual characterization of a property as a qualification condition to study convergent ray for solving of computational methods for solving non-convex feasibility problem. Actually, this paper recently significantly improved by Rubetzky, Yufei, and Lewis, when the transversality is replaced by the intrinsic transversality. Okay, so I just mentioned the three group of property. So now we talk a little bit about the metric characterization. Actually, the characterization follow directly random definition. And we will see that the three inequality follow the same pattern. It provides the upper bound for the distance from some point to the intersection. So let me explain carefully just for example. So let's take a look at the subdifferentiality, the middle one. So if the set is subtraversal, then we have this inequality satisfied. So in general, calculating the distance between x and two intersection is difficult because actually we do not know the intersection. But if it's subtraversal, so we can know the upper bound distance by this maximum distance. And the right hand side is easily to compute because we just need the information of the individual sets, not intersection. So this one is more easy to compute. So that's the reason why this estimate is used intensively in projection methods to study feasibility problem, because the feasibility problem is the problem of finding the intersection. So if we know some estimate in terms of distance to the intersection, then we will get some good convergence rate. So the idea applies similar for the other one. But in my understanding, when study computational methods for subdifferentiality, people usually use this inequality. But for transversality, instead of employing this metric characterization, people use the normal characterization in terms of normal cone of this property. So it would be good if we can employ this property to study the conversion rate of computational methods. So I believe that we can get some equivalent result, but it would be good to make the picture clear and complete. So it would be good to pay some attention in employing this metric characterization to study computational method. And in fact, we have formulated several metric characterization, but in here for simplicity, I just pick up some characterization. Okay. So now we consider the convex case. So assume that the function that the set is convex and phi belongs to this C delta. And actually phi is not necessary to be convex. It can be non-convex. So we prove that in a convex case, the characterization of the semi-transversality can be significantly simplified. So remember, in the definition, we require this in this non-emptiness. How for our rho belong to 0 to delta, but in the convex case, we just need it hold for the upper bounds rho. It is significantly simplified. And similarly, we have the same characterization for phi transversality. Instead of it's hold for our rho from 0 to delta 1, it just hold for the fixed the upper bounds. Unfortunately, we do not have the simplified version for subdifferentiality. So it would be good if we can find a simplified version for this. Okay, so this is the geometric characterization in the convex case, and it's clear that we can write in a different way in the metric term. Instead of in the metric term, we remember that in the right hand side, it usually the the phi at the maximum of xi, but it's not just delta. Okay. Similarly for phi transversality, instead of phi of max of xi, it's now just delta. Okay, in the convex case, we prove that semi-transversality implies transversality. That's a very interesting result, in my opinion. So specifically, if the collection of sets is semi-transversal, then it is C transversal. It's a slightly different function, and the function C is related to the function phi in this way. And in the particular case, when phi is the power function, we have the equivalent. It's not quantitative equivalent, but qualitative equivalent. The set is semi-transversal, if and only if it's transversal. Because in general, we always have transversality implied semi-transversality. Now in the convex case, we have the inverse implication. So we have equivalent. And now we declare that in the convex case, semi-transversality will imply subtransversality, and also imply, of course, imply the intrinsic transversality, because in the convex case, subtransversality is equivalent to intrinsic transversality. So yeah, I think this is it's an interesting result in a convex case. Okay, now I'm going to talk about the slope. Given x is a matrix space, and the function f is a standard real value function, and the point in the domain. So we define the first term like this, lim sub of this, and this one is the subprimum. So the second one we call it non-local slope, and the first one we call slope. The slope was first studied by Di Giorgi, Mario, and Toss in the paper in 1980. Actually, the slope is usually called in the literature as the strong slope. But when I read the paper, I haven't seen the strong name. And I also sent the Italian version of this paper to my associate supervisor, David George. He very good in Italian, and he also confirmed that they know strong in the terminology. So we decided to call it the slope instead of strong slope, just to make it clear for them. Okay, so the slope provide the rate of step descent of the function and the point. And when the function is smooth, of course, when in this case we need the space x to be norm vector space in order to define the ratio differentiable. In this case, the slope is equal to the norm of the derivative. And it's clear from the definition that if f of x is greater than 0, then we have this equality, because this one is local and this one is global. So it's clear from definition. And when the function is convex, we have this the equivalent. Actually, this is very important. It's similar, but important result for the study, because in order to study necessary condition, we need this property. Of course, we need the space to be norm vector space in order to divide the complexity. And we also prove the chain rule for the slope. In this case, the derivative of the function at this point is positive. So it's very elementary. Okay, just for my curiosity, I want to know who is the first person use slope in study metric regularity in error bars and transversality. And I found out that in this chapter in 2001, Alex Giffey mentioned that mentioned the paper of Ajay, Coderivative, and Lucetti. He mentioned that this paper improved some result in the literature, but the most fundamental contribution of this seems to be the very fact that the slope of Dijoji Marantos for the first time appear in the context of metric regularity theory. Of course, we can say the term different. This paper published in 2002, but in this chapter, information is a submitted paper will be in submitted paper in 1999. Actually, before that, Alex Giffey had already studied metric regularity theory at about, but instead of using primal, he employed the flag subdifferential to as a sufficient condition for error bound of the Lipschitz function. But this paper of Ajay and Kovarak and Lucetti show that before we go into dual, it is meaningful to study Riemann first. And actually it's meaningful because we already see the slope is a derivative-like object. When the function is smooth, it equal to the norm of the function, a norm of the derivative. So it's meaningful to consider Riemann before we into dual. Okay, this is the necessary condition for semi-transversality. In here, we require not the convexity for the set and also the function phi. Let gamma be this constant. So if the set is phi semi-transversal at the point, and then we have this inequality satisfied. Okay, so now in the denominator, we employ the parametric norm depend on gamma in this way. And actually, the left-hand side of this inequality is the slope of this function. This is the sum of the phi of the maximum of the norm and the indicator function of the rod axis. Of course, the function is convex because the set is convex, so the indicator is convex, the norm is convex, maximum of the convex function is convex. The function phi is convex and also it non-enriching because and also it increasing. So this function is convex. The sum of two convex function is convex function. We get this result from the definition of relativity. We just assume that the relativity is satisfied, and then we get some estimates in terms of instead of local, instead of slope, we get non-local slope. So we need the convexity here actually to make the non-local slope equal to the local slope. So from the definition we get, we don't have limb here, but in order to get limb sub, we need to impose some convexity assumption. And gamma here play actually an important role. If we look at the definition of the gamma of the norm, so if this inequality hold for this gamma, then it also hold for any constant smaller than gamma, because gamma belongs to the denominator. So it's clear. The left-hand side is the slope of this function at the point x bar and x bar. If we replace x bar, this one the x bar, this one the x bar, this one the x bar, we get the omega I equal to omega equal to x bar, and then this one will be phi of max of xi. This one equal to 0 because x bar belongs to the recess. So we get this one. Okay, so the left hand side is just a slope of this function at the point x bar, and x bar, and the function is convex. Okay. So in a smooth case, when the function phi is convex, we can apply the chain rule that I mentioned before for the slope. So we can take this. We can have a little bit a simplified version, but it's equivalent. In this one, we don't require the smoothness assumption on phi, but if the function is smooth, then we have this simplified version. And this is actually in the linear case, this is the result we also use. So similarly, we get some result for subdifferentiality. It's also necessary. And in the non-convex case, this condition is also sufficient. So when it convex, so we have the complete characterization for phi subdifferentiality. Similarly, apply the same techniques, we get some result for phi transversality, and this result is this condition is a bit stronger than the necessary condition for semi-transversality. This is understandable because transversality is stronger than semi-transversality. So this one is stronger than the corresponding one. So again, it is just a slope of some function. I just mentioned for semi-transversality, this one is similar. We can define some function. That's the phi of max of something plus the indicator function of the dot axis. But I just mentioned for semi-transversality for the simplicity. Again, we can also apply the chain rule for this one. Okay, so now we go to the dual. In convex, the dual necessary condition, we just work for convex set, convex function. So we just to mention some basic fact about the convex subdifferential. This is a very standard definition for a convex subdifferential. X here norm space. X bar belongs to the domain, and we have the representation of the convex subdifferential. In convex case, we have the exact sum rule. It's very nice. We also prove a chain rule for the Breze and also Clark subdifferential. An interesting fact about this chain rule is that actually there's some result about this chain rule in literature, but what we did is our proof just depend poorly on the definition of the subdifferential. It's very elementary. So in the special case, when the inner function is convex, so we have a chain rule for this. And we also employ the following one. So let's see it defined in this way. It's the maximum of some linear function when AI is a given vector. And we consider the point x1, x2, and x such that this the value of the function is positive. And then we will have the representation of the subdifferential of this function. So actually, this is just a direct computation because the function is rather simple. It's just the convex. This is the composition. The norm is convex, so the maximum of the norm is also convex. So this is the composition of the convex function and the linear mapping. So by direct computation, we will have this representation of this function. So we will need this result later. I also employ some basic fact about convex number cone. This is the definition for the convex number cone. It's very standard in convex analysis. So we have some connection. The subdifferential of the convex function is connected with the normal cone in this way. This is the normal cone to the AB graph of the function at the point x bar and fx bar. And the normal cone to G omega at x bar is the subdifferential of the indicator function to G omega at x bar. This is what we needed. And the normal cone to the rod axis is equal to the product of normal cone. Okay, that's what we needed. So now, the idea is that, so let's talk first about this result. So assume that the function is convex, phi convex, gamma in this way. Gamma, as we mentioned before. So if the set, if the classical set is phi semi-transversal, then we will have that the distance from 0 to the subdifferential of this function greater than 1 for our x satisfy the condition. In here, the dual norm, the distance is defined by the dual norm in this way. This is actually the norm, the dual norm corresponds to the primal norm we defined before. Remember that in the primal norm we have the constant mu. In here it the constant gamma. In here we have 1 over gamma. It is just the direct counterpart of the primal norm. And remind that the function f is defined this way. Okay. So the idea is that how can we get from primal condition to dual condition in terms of necessity. So normally when we work with sufficient condition, so if we want to go to primal slope to dual, we usually prove by contradiction. We assume that the regularity is not satisfied, and then the slope is not satisfied, and then we get some result that some function attain the minimal at some point, and then we apply the Fekma rule. We have 0 belong to the subdifferential, and then we apply the sum rule. It can be Fuzzy sum rule for Rayleigh subdifferential, or exact sum rule for Clark subdifferential, because in this case we don't have complexity, and then apply this sum rule we get. So in general, in proving sufficient condition, we prove by contradiction. So we will see that in proving the necessary condition, the context is different, but it's similar actually. So I will provide a short proof for this proposition to see how we can go from primal to dual in terms of necessary. So in order to prove this red inequality, we just need to prove that we pick any subgradient belong to this set, and we prove that the norm of this subgradient depend on gamma for any subgradient greater than 1. That's what we need to do. So this is the proof for this. We take any subgradient belong to the subdifferential of the function f. So the first one is just the definition of the dual norm. Of course, we have many equivalent definition for the dual norm, but I just to choose this one. Okay, so this is the supremum, and then we go to this one. Because this is considered for all u, 1, u2, and u are different from 0, so we can replace this by u U1 minus x and U2 minus x and U minus x. It's just another point. And also because it's the global version, it will greater than the global version. So this one greater than this one because the global greater than the local. And then because this subvariant is the element of the subdifferential of the function f, so the this numerator will be greater than this numerator, just because the definition of the convex subdifferential, because the function f is convex. The denominator is the same. And each one we just replace the function f by the definition of the function. And this is the slope condition that we already get. And this one greater than 1 because we already proved. So the proof is very elementary. So but I think it's interesting. And we can apply the same technique for subdifferentiality and transversality. Okay, so this is an intermediate result. This is the main result for the dual sufficient condition for semi-transversality. So the function is convex, the set is convex, and in here instead of gamma it is mu. Mu actually the inverse of the gamma. This is because the definition of the dual norm. So let's take a look at so if the set is semi-transversal, then this inequality satisfied for our x star satisfied the condition. So just remind that we have the function f here. So I will explain where some of the elements come from. So we have the first term is the derivative of the function phi. So this one get when we apply the chain rule to this function at the point x bar, we apply the chain rule. And the normal con here come wrong when we apply, we using the fact that the subdifferential of the indicator function is the normal con. So in here we will have the normal con of the rod axis, and again the normal con of the rod axis is equal to the product of normal con. So we get some normal con here. And where this condition come from? This condition come from when we apply the representation of the subdifferential of this maximum function. And just remind that we have this one. This is the representation of the maximum, the representation of the subdifferential of the maximum function. So we have something like this. Okay, so that's what we get. And this one is the condition go along with the slope necessary condition. So yeah, everything is straightforward, and anything in the normal con here is in terms of convex analysis. Similarly, we have some result for subdifferentiality. And again, we apply the same technique. We apply the some rule to some convex function. Of course, it's different. The function is different from semi-transversality, but we get some result. And this is one for semi-transversality. And we just apply the same technique. Okay, so now I will talk about the connection between transversality and regularity. So let F is a circular mapping defined on matrix space in the point in the wrapper function. So we have some property. The first one we call semi-regularity. So if inequality holds for our y bar satisfy the condition, So in the linear case, this property is studied by Alex in paper 2005, I think. And recently, this property has been employed to analyze the convergence trace of Newton methods in the paper of Alex and his co-author. So the other one is very well-known property, subregularity. It's very standard. We impose the restriction for the inequality when the right-hand side is smaller than delta, just to make sure that want to make the quantitative equivalent between transversality and regularity. So actually, this condition can be wrote, but in this case, we will have some different constant delta. And in here, the delta 1 and delta 2 is different. The contribution is different. And this one is the phi regularity. It is uniform version of the subregularity. Instead of requiring it hold for our for fixed y bar, it hold for y bar near it hold for our y near y bar. So we impose this condition. Normally, it's required hold for our x belong to some neighborhood of x bar, and y bar belong to some neighborhood of y bar. So we impose a slightly different condition just to make a clear equivalent between regularity and transversality. So, and they are very well-known property in variational analysis. Okay, here the connection. So let x null space given to set in the point x bar. So we define the circular mapping like this. And then we see that the point x bar belongs to the graph, s bar 0, 0 belongs to the graph of the function. And then we will have that if the collection of sets is a phi transversal, then it's a if only if the circular mapping is phi regularity respectively at this point. So actually we have a clear quantitative version. Some constants are carefully computed, but for simplicity, I just provide the qualitative version here. So the other way around. So let f is the function defined norm space. So remember that in matrix regularity, we just need the matrix space to define the property. But in order to make a clear connection, in order to make a connection with transversality, we will need the vector structure for the circular mapping. So we define omega 1 and omega 2 in this way. You got omega 1 in the graph of the circular mapping, and omega 2 is the product of the x and y bar. And we easily check that x bar and y bar belong to the intersection of two sets. So let's find is a given function, and we define function c in this way, phi of 2t plus t. We show that if the function is phi regular at the point, and then the color subset is c transversal respectively at the point. Again, we also have the quantitative version, but we mentioned the qualitative version here for simplicity. And as consequent, this one in the Hilda case is just a slightly different constant. So let's find a given again, and we define c in this way, phi of t over 2. So if the collection of sets is phi transversal, then the circular mapping is c regular respectively. So this is the reference of my talk. So based on the joint work with Alex and Harpoon. So thank you very much for your attention.
Thank you, King, for your nice presentation. And everyone, I believe, is impressed with the long list of publications on the topic. And I can add actually that what King was talking about today, it's a small portion of what he has done in his thesis. So he is an expert on all these things now. So King is generous enough to leave us 9 minutes for discussions. And let's use this time. Do we have questions from the audience, comments? I don't see many questions raised, which means, Tao, please. Tao is another expert in this area. Please,
thank
Tao.
you. Thank you for a very good talk. More explanations. Thank you. I just have a question about your relationship between transversality properties of collection of sets and regularity properties of set-value mapping. I see on the result for transversality properties, you only have some kind of convex assumption on, but for the later part on the regularity property, I don't have that.
Yeah. Actually, we mentioned we make a connection between the regularity and transversality in the convex setting. We do have, and this result already published, I think, in the paper on this paper.
So in this talk, you only mentioned the transversality property of collection of sets, but you don't formulate the similar result for set value mappings.
Yeah. This result in this paper in the number 2 we published on positivity.
But not mentioned. But you didn't talk today, no?
Yeah. Because I think we don't have enough time for more result. But we do have the connection between transversality and regularity in the convex setting, and in this paper on published on positivity.
Yeah. So for the result on necessary condition, so the convexity property is important. Is it right?
In general, I think the sufficiency and necessity is equivalently important. So
no, I mean because on the results you present today for collection of set, I see the convexity assumption appear on
yeah.
That's why I raised a question about.
Yeah, the convexity is very important assumption. Why we need it? Because let's take this result in here.
Yeah.
At the depth, when first we assume that the property is satisfied, we get some estimate, but not with no convexity.
Yeah,
but then we need the convexity to formulate internal slope. If we don't have convexity, we just have non-local slope condition. And when the convexity is imposed, we will get the local. And from the local, then we get to the dual. We cannot get the dual from the non-local.
Okay.
We only yeah.
Okay.
So we do have the non-local necessary condition in non-convex case. But if we wish to apply the slope, we need the convexity. It's very strong assumption. Yeah, it cannot be wrong.
Okay,
Okay.
Thank you. Continuing on Tao's question, or actually on your response to Tao's question, Cuong, you mentioned that necessary conditions, you made a strong claim a minute ago that necessary conditions and sufficient conditions are equally important.
Yes, yes.
And I'm not absolutely sure about that. The majority of people are developing sufficient conditions and not so many people working on necessary conditions. Why do you think that necessary conditions are important?
Just like a simple example as a Feynman rule. We can, in order to check whether point is the minimizer or not, we first need to restrict the candidates by considering zero belong to subregion of the function. So I think the idea is applies similar for this property.
King, there is a big difference here. You are comparing with necessary conditions of optimality. And optimality is an opposite property to regularity in a sense. So necessary conditions for regularity, they translate into sufficient condition for some kind of optimality or stationarity. Why do you think that such conditions are of importance?
Yeah, first I need to believe it's important, and then I will do it.
First you need to believe. Okay, actually I accept this answer. Thank you. We need believers.
Yeah, and then just curiosity.
Oh, and curiosity. Okay, it's advice to everybody in this room.
Yeah.
Great, thank you.
But in some case like this, like subdifferentiality, this necessary condition is also sufficient. So it's really nice result actually.
When you prove that something is necessary and sufficient, this is great, of course, which means that your sufficient conditions are not too strong. Okay, let me interrupt at this stage. We have a nice question in the chat. Do you see the chat, Cuong?
No, let me take a look.
If any problems, I can read it to you.
Okay.
Okay.
I can.
You can, no? No. Okay. The question is from Pham, and he asks, how about if you consider sets, maps, which are semi-algebraic, that is with a special structure? It means that we change convexity by semi-algebraic. So do you think that it is possible to replace your convexity assumption in your theory with that of semi-algebraicity?
Actually,
can it be done?
Yeah. I see the question from Professor Phạm Tiến Sơn from Vietnam, so I know him. Yes, I think so. Actually, I am trying to move my attention to the general setting, to some particular setting like semi-algebraic. And one of the reason is that I read one of the paper of Professor Phạm Tiến Sơn. He also gave the talk last year on this seminar. He studied some Hilder regularity on of the semi-algebraic separable mapping. So I believe that we can do something by moving from convexity to semi-algebraic. Thanks for the question, but it also an good idea. Yeah, I believe so.
Okay. So it's worth thinking about problems with special structure. This is an important direction. Many people work on this.
Yeah.
I don't think we have more time for questions. Let me formulate a question which I wanted to ask, but I will not ask. I believe many people in the audience who are listening to your talk were thinking about this question. why do we need nonlinear problems? Why do we need nonlinear transversality properties? So if it would be good if next time you talk about such things, you explain why nonlinearity comes into place. So I will not ask this question, we don't have time. Do we have one more very quick question from the audience? If not, then thank you very much, King, for your presentation. And indeed, in my opinion, you did very well. You explained things very well to me, at least, what you were talking about. I hope that others in the audience also liked your presentation. So thank you, everybody, for coming to this seminar. And we meet again next week at 5, right? Same time.
No, I think it will be